Hello and welcome. In this video, we are going to discuss the global maximum and global minimum of a function on a closed interval. Recall that the derivative of a function at a point A is actually the same as the slope of the tangent line at that point. If you look at the function y is equal to x squared plus 1, this quadratic function, the slope of the tangent line, this blue line at this point, is the same as the derivative of the function at this point. And recall that the slope of this function is the ratio of delta y and delta x. And this ratio delta y over delta x, if the limit of this ratio where delta x goes to 0 is the same as the derivative of the function at this particular point. However, if we have a function such as this function where we have a sharp turning point and we take the tangent line there, we see that the tangent line is actually a vertical line at that point. And recall that the slope of a vertical line is actually not defined because delta x is 0. Delta y over 0 is not defined, hence the limit as delta y over delta x when delta x goes to 0, since delta x doesn't change, is not defined. Therefore, the derivative of this function at this sharp turning point is not defined. Let's have a look at some further examples. And here we have a turning point which is a smooth turning point. Therefore, the derivative of the function at this point exists is in fact 0. While in this sharp turning point, again, we will be having a tangent line, which is a vertical line, hence the derivative is not defined. In this function, we have this turning point where the derivative exists and is equal to 0, while in this point here, we have a sharp turning point where the tangent line will be a vertical line, therefore the derivative, which is the same as the slope of the tangent line, doesn't exist. And in this turning point here, the derivative exists and is equal to 0 because this is a smooth turning point. A critical point, an interior point of the domain of D of the function y is equal to f of x, is called a critical point if at this point either the derivative is defined and is equal to 0 or the derivative is not defined. If you look at this example, we have two critical points. One is this sharp turning point where the derivative is not defined, and this smooth turning point where the derivative is 0. Hence, at a critical point, either the derivative exists and is equal to 0, at which we will be having a smooth turning point, or the derivative doesn't exist and it's not defined, where we have a sharp turning point. If you look at this example, here we have a sharp turning point, therefore the derivative is not defined. And here we have a smooth turning point where the derivative exists and is equal to 0. Therefore, we have two critical points. Now, let's turn to finding the global max and mean of a function at a closed interval. Take the function y is equal to f of x, which is defined and continuous on a closed interval a and b. Then, following extreme value theorem, the function is attaining its both global minimum and maximum in this interval. To find the global max and mean, we first evaluate all critical points and endpoints, and then take the smallest and largest values, which would represent then the global max and mean, noting that you might end up having more than one global max or mean. Take the example of the function y is equal to x squared plus 1 defined on a closed interval -2 to 2. So you see that this function is defined from -2 to 2, and this is x squared plus 1. Let's have a look at critical points. Do we have a critical point? Yes, we have a critical point down here, which is a smooth turning point for which the derivative is 0. So we take the first derivative, which is 2x, and we let it to be 0. From this equation, we find that x is 0, and then we insert 0 in the equation of the function to get y to be 1. So therefore, that critical point is actually 0 and 1, attained at x equal to 0. Then let's check the endpoints. F of minus 2 is 5, f of plus 2 is 5. So those are the values of the function at two endpoints. Then putting them together, we get the following. F of 0, which is a critical point, is 1. F of minus 2 is equal to f of 2 is equal to 2. So therefore, the smallest value is 1, which is attained at x equal to 0, which is a critical point, which is an interior point. Therefore, the global minimum of the point is attained at x equals to 0, while the global maximum of the function are attained at minus 2 and 2. So both of them are representing the global maximum, which is the largest value of the function at this closed interval. Let's have a look at the function x cubed x squared plus 2 defined on a closed interval minus 1.5, 0.5, which is this function here, from minus 1.5 to 0.5. If you look at the graph of the function, do we have critical points? Yes, we have one turning point here, which is a smooth turning point, another turning point here, which is again a smooth turning point. Therefore, the derivative of the function at both of these points exists in 0. Let's find those points. For that, we take the first derivative and let it to be 0, because as we said, at a critical point where the derivative is defined, which is a smooth turning point, the derivative is 0. So therefore, we let the derivative to be 0. The derivative is 3x squared plus 2x to be 0, and then we solve this quadratic equation. Taking x as a common factor, one of the x's would be 0. The other x would be minus 0.7. Then we find the corresponding y values for x1 and x2 to get f of 0 is 2. That's this point here. And f of minus 0.7 is 2.147, which is this point here. In the second step, we check the endpoints. The endpoints is f of minus 1.5, which is 0.87, this point here. The right end of the graph is f of 0.5, which is 2.37, which is this point up there. Then we compare these four values to 2.147, which are critical points, interior points, and 0.87 and 2.37, which are endpoints. We take the smallest one as the global minimum, and we take the largest one as the global maximum, and it turns out that the global maximum is attained at 0.5, which is then 2.37, which is the largest value, and the global minimum is attained at minus 1.5, which is 0.87, which is the smallest value that the function takes.